Hi all, my name is Vladimir. I am a developer of Linux Studio plugins, and today we are starting our pilot stream of the video channel Nightly Code. So it's 0 o'clock in the Moscow time and about 21 o'clock UTC. Today we will try to improve the Linux kernel driver of the Focusrite Scarlett audio device plugin series. And the first comment which I got today is that the description of the video is missing the M letter. So I've already added it to the description. So that's okay now. Please let me know how good the translation is. I mean the video and the audio. If all is okay, then we can continue. And I will first of all describe my setup. So for correct development of driver, we need to do some reverse engineering of the device, or the protocol between the host and the audio device. And the virtual machine, virtual box will help us in this. So I have a virtual machine. I have a 18i8 audio device. And I have additionally a laptop, Asus TUF Gaming, my primary laptop, which I use as a device at which I can try the Linux kernel and test it. So, first of all, I have a virtual machine with Windows 8.1. This is fully licensed Windows Pro, I believe, version. And at this moment, we see that there is a Focusrite control service installed at this virtual machine. I already have the device connected to the USB, but I didn't route it to the virtual machine. I can do this just by clicking here and routing the corresponding device to the virtual machine. So let's look at this. Now the virtual machine found the device, and the Focusrite control software has connected to it and displays the configuration of the device. The main problem was that the vanilla installation of the VirtualBox doesn't allow to route the USB traffic to the virtual machine. So I was required to install the extensions from Oracle site, and then I just set up these extensions to the virtual. I just loaded these extensions into virtual machine, and all started to work. I just need to show this probably. So if I just launch preferences, and there are, oh no, not here, here. Sorry, some part of the interface is in Russian since I'm native Russian speaker, but I probably think that all is clear for you. So this extension file was just installed, and now I can, after install this extension file, use the settings of virtual machine and set that it should use the USB forwarding using the 3.0 XHCI controller. With the 2.0 OHCI and EHCI controller, that didn't work. It works only with the USB 3.0. So Anyway, we see that the device is currently functioning, the software has connected to the device, and how we will perform the reverse engineering. For that purpose, we have a dedicated tool. It is called USB Pcap. I just will launch the cmd command line tool and switch to the corresponding folder where the USB Pcap was installed. So it is cd c program files, and then cd USB Pcap. Yes. So what's here? Oh, here's the main software. Is called USB Pcap cmd.exe. So I can just launch it. And what we can see, it scans for available USB hubs and allows us to switch the hub that we want to use to capture the traffic. We have the only one hub here, and that's why it's just easy. We need to enter the one and the name of the file where we want to store the protocol dump. First, when I was using the virtual machine, there was also the mouse visible here. So I was required to switch mouse from USB to PS/2 to not to have mouse, some garbage from the mouse in the protocol dumps. So now I will have just clean protocol dumps that are related only to the audio interface, the exchange between the program, the software, and the audio interface, or the exchange between the driver of the Focusrite device and the Focusrite device. So we'll stop at this moment and check the second moment. We already have a laptop, and I will use a remote connection via SSH to this laptop. What I did yesterday to prepare for the first streaming, I have just built the new 5.15.12 kernel, which already was patched by me to be compatible with hard real time. And I already compiled it, and I already installed it, so you can see this. We can see this by just entering the uname -a or -a in the terminal. What we will do? Additionally, I have already mounted the home/work directory to my local machine via the SSHFS, and so I have already the access to this tree from the my mount point. This is just simply done by such command, if you see it right. I don't want to enter it every time, so I just saved it in a bash script, and there is one liner. First of all, we need to disconnect the device from the virtual machine and try to connect the device to the laptop and check whether the software, the driver, the kernel sees the laptop. We can use this in the following manner. We just will switch to super user and show the dmask output. This is the kernel messages, which are printed to the buffer and then displayed on the screen when we call dmask. We can clear the output. I believe there is a -c flag. So there's currently none. And we can follow the current output. Uh, there's a Russian comment that says that there are many Russian people looking the translation, and there are non-Russian people in the watching the translation, the stream. But I believe the channel will be more popular if it will be English spoken, not only Russian. Anyway, anyway, thanks for the comment. I've stopped at the moment that we can watch in real time what happens with the mask just by entering the dmask minus b minus w. So now all what happens and with the kernel, and if more new messages appear, then we will see them. So now I will take the microphone off and switch the cord from my desktop PC to the laptop, and we will find that the device will be visible. So I've connected the device to the USB, and we already found that the driver has found it and already enabled. What we can do now? We can do one more connection to the laptop. And we can launch the ALSA mixer. We press F6 to set the device. It's a Scarlett 18i8 USB. 18 means 18 inputs, and 8 means 8 outputs from the that's how the devices are numbered. So, and what we can see here, there's master volume. It doesn't work at this. Oh, I don't rotate the wrong knob. Yes, it works. Key. I rotate the hardware knob. I rotate the hardware knob on the device, and it works. There's a speaker switching option. There's a line volume of the line. There is mute. I don't understand why the mute isn't mute. It should be unmuted, or it works in the reversal, but they are not muted. I don't know why they are muted at this moment. It seems the device is wrongly restoring the state. The driver is wrongly restoring the state. So there are line inputs. There are volume controls that allow us to set the software volume control. So when we rotate the hardware knob on the device, it won't affect the loudness of each channel. And there is hardware control that means that when we rotate the knob on the device, the volume will become additionally automatically adjusted. This is done programmatically by the driver, as far as I remember. There is some related to mixture. Some volumes on the mixture are set. Some volumes are resetted. So, okay. What's more? There are routing settings. So there are 8 outputs, and for each output we can specify the corresponding input. There are different inputs available for the 18i8 device. There are analog inputs, PCM inputs. There is also loopback, is ADAT input, and I believe is PDF. So there are many options. There's additional dim and mute buttons, which are, I believe, available here. I look at this. I don't see them on the device. There is sync status. There is PDF status. I don't see there. Oh, maybe this is captures. There are captures. Oh, I think I need to switch to all settings. And there are additionally available buttons like 48 phantom power. There are things additional available like instrument or non-instrument switch between I believe for each channel or for some of the channels. Yes, there is instrument switch, there is part switch padding, but I don't see here any instrument padding switches in the driver. I don't see them. That's line in level. So I can switch line to instrument, it works, yes. It shows with the red lighting LED on the device. Yes, padding, I don't know how to switch it. The device allows to pad, but I don't know how to switch it with the also mixture. Oh, so with the space. Okay. That's interesting. Okay. Okay. Yes, it seems to be working right. And what's more? So, and I believe there should be also gain halos. What is gain halo? Gain halo is the light, the color of the light, which is distinguished to each input, and works like a level meter. When we speak above, there are different settings. As far as I remember, the minus, the all signal below the -6 decibels is shown because with one color. Above 6 and below 0 decibels is shown with another color. And the last color is used for the signal which is overloaded or overdriven and is above, and it has peaks above 0 decibels. So I don't see the gain halo settings here. Probably it's missing. But that is a good feature anyway. Oh, there's a phantom power persistence settings. Okay. Phantom power persistence means that when we turn the power of the device off and then turn it again on, the 48 volts of current will be persisted as before the switching the power off. So we see that the driver works, that it allows to set many switches and many options. But the main problem of this driver is that it doesn't allow to do all the things that allows to do the Focusrite control device. For example, Focusrite control has a mute option for any input. It has mute option for any mix channel. It has, I believe, solo panning options or something, and also it has a gain halo settings, which is missing here. So we need to explore the driver now and compare it with the previous version that was initially improved by me. There was additionally one developer of driver, Geoffrey Bennett. This man was pretty good. He designed many features of the driver. Then I took his driver and improved it. And then Geoffrey took some my changes back and finally sent the changes to the upstream. And these changes have been already introduced in the latest kernel. Anyway, not all features that I was introducing were backported by Geoffrey to the original driver. And one of them is that the driver doesn't read the so-called software in configuration area of the device. What's this? I will show soon. So I need to open some editor like Kate, for example, and open the new version of driver and the old version of driver, or my version of driver. So there's MNT1, and it is here in the sound USB subfolder, and it is called Focusrite Scarlett Gen2.c. That means that this driver was originally written for support of Gen 2 devices and then extended to support and Gen 3 devices too. So here's the original, the 15.12 or 5.15.12 kernel driver version, and my version. I'm storing it somewhere else in my I will open the debug driver since it contains many additional messages that are useful for debugging the driver. So I will open it here. This is my driver, and this is Geoffrey's and and my collaborated driver. So the main changes what I can look at this moment. I really don't know how many things we will do at this night. Probably I need to be adopted to the new driver and learn the changes, all changes that were made for the driver. But I believe we will do something at least to improve this. Anyway, for example, we have here this array for converting floating point levels to the integer levels, and here there are missing. So the driver doesn't read the configuration error of the device. There are some additional enums. There are some additional constants. So there are additional constants additionally commented by me and described. I love many comments since it will help us to understand in the future what happened when we have written this driver. So what's more, there are configuration, there is device info, there device descriptor. We have device descriptors here. Each device descriptor is has the full description, the capabilities of device and additional features of it. There is Scarlett data. This is the main structure that is used for managing the device. And here it was called the Scarlett mixture data, so the name of the structure has been changed. Here's the configuration of the device, I mean the description of devices, and then the routines. So the list of supported devices is the following. This was taken originally from my version of the driver. And thanks, Geoffrey, that he has taken it to long. Okay, here's. Yes. Then the volume status structure. For additional information, we will learn and figure out how it is working here. And Scarlett 2 dump buffer. The first function. That function was written by me to simply dump some buffer data, and it was carefully used by me for debugging. So we will take this function as soon as possible into our new version of driver. This function was written by me too. It wasn't ported here, and so on and so on. So what we need at this moment to look into the driver initialization code, and here we see that the device is initializing, creating additional controls in the mixture, and here all the routines were called that do the stuff, and that doesn't differ much from what was previously, except that some code was split. Some code was split into additional function, I believe. Oh, the additional function was implemented. I believe this is for compatibility with the new kernel. Okay. Anyway, what we can do now, we can just switch back to Windows and try to capture something and explain the workflow of the reverse engineering. So I'll switch the code now and go back. Okay, let's look into Windows 8 machine. Oh, it already sees the device. And what we can do at this moment, we need, first of all, each protocol dump starts with the connecting to the device. So first of all, I need to disconnect the device, and I do this. Why in such manner? It's very easy to find out the changes when we get the when the device is connected. The driver of the device requests all information from the device, so we can read some protocol messages, interpret them, and make an image of the configuration space of the device at the start. And then with each with each following message from the device to the driver, or the driver to the device, we can see the changes between the current state of the device and the new state of the device. And in such manner works my special tool that decodes the Pcap files and allows to analyze them. So first of all, we need to launch the Pcap capturing. USB Pcap cmd.exe. We switch one and name the Pcap as Scarlett 898 mutes. We will check how input mutes are working, and the extension is Pcap. Okay, yes, hello. Fine. It has started. And now we can connect the device. It has connected. The driver has found the device, and now it seems okay. We need to wait some time, a bit, I believe 10 seconds, since it is hard to distinguish the initialization sequence and the changes made by user. So we need to have a time gap between the initialization of the device and the actions actually made by the user. So it's pretty enough enough time gap, and we can just switch mutes. We will do the simple thing. We will just use all inputs and mute them and then unmute them. So let's do this. Are there more? Yes. Okay. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12. 12 outputs. Oh, we are working the outputs now. Yes. Yes, there are outputs. I was wrong. Yes, you are right in the question. There are outputs. So, and now we will unmute them. Unmute, 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 and so on. So, it's pretty enough, and we can now quit the USB Pcap by pressing Q. Now we need to transfer the Pcap file to our host machine, and that's pretty simple. That's the mounted network device, and local disk, C program files, and there's USB Pcap. Yes, here it is, and we'll just use this to copy here. And now we're available to launch our decoding tool. I've already made a symbolic link to the shared folder, and so we have it in our development tree. Here it is. Here is the file. It looks so. It's binary protocol, and we have a simple tool. I call it decode. It's one file that allows to decode the protocol messages from the device and driver. And I already have a script run sh that allows to run the script and specify the input file to process. So we'll do this. I'll run sh. I'll do this in console. Run sh ff Scarlett 18i8 in mutes pcap. So it will be in, but you should consider this out mutes. Okay, it has done, and we have 4 files at this moment. The clean log is the overall the decoded log is the overall messages between the device and the computer. So there are many garbage messages that we all don't need, and these messages are cut out by the script and saved to clean log. So we will look at the clean log, which is more interesting for us. So I believe I'll launch Kate for it, and disable line wrapping, and look into the messages. So here are the messages from the host to device, or from device to host. This is an initialization sequence. We don't need to look at it now. And at the left, the leftmost column is the time since the capturing has started. or the exchange has started. So we need to find messages which are delayed more than 10 seconds, and there will be changes found. So we need to look. Oh, here starts. Okay, do you have the device connected? Yes, that's good. So we did the muting of outputs in the following manner: the monitor output 1, monitor output 2, analog 3, analog 4, and so on. And then headphones, and then SPDIF, loop back. So the first change is related to the monitor output 1. So you can see that each input is configured in mono at this moment, and we can configure two near outputs as a stereo. That is additional feature, and we will probably look at it in further streams. In this stream, we'll just look at how mutes of outputs do work. So there's a message that is sent from the driver to the device called set data. The offset is hexadecimal 5C. The only one byte is changed, and it's this change from 0 to 1. What my utility does detect. And we can now create additional file and write. So the offset is I think I can switch. I switch in following manner and right here. Okay, so where's the first change? I'll leave. It's here. Okay. The hexadecimal 5C 00 to 01. And additionally, we have additional messages that perform the routing of the device. So here we can see, since the device has 3 routers, the first router for the 48 kilohertz, the second router is for 96 kilohertz, and the fourth router is for 192 kilohertz. So the MUX 0 is the for 48 kilohertz discretization frequency, the MUX 1 for 96, and the MUX number 2 for 192. So we can just take the state that was set and remember it here. I believe we have some temporary project, and we can new file routing after txt and paste it here and replace with regular expressions. Oh yes, regular expression. We need to replace spaces with new lines and replace. Yes, it seems to be okay. And the previous state we can take from the previous message set MUX, and we need to look at this here and find the set MUX message before set MUX. I believe this with space. Oh, not with square bracket open. Here it is. This is the previous set MUX message that was sent when initializing the driver, and we can use the mapping this mapping to compare with the new mapping that was shipped to the device. So let's take the clips, new file, and routing before txt. Okay, now we can compare them one to another and just take 1, 2 and compare with each other and see what has changed. We see that only one line has changed. This is decimal. The 18th, starting from numbering from 0, the 18th connection point has changed from source PCM1 to off, and the destination is analog 1. So this is analog input 1, and the source is routed to the special off line, the line that always delivers zeros to the output. So as we see, when we press mute, not only the configuration space of the device is changed, and also the routing is changed by the driver. We need to remember that. And now we can grab all messages and look at the configuration. So let's go back to the gate. Where's gate? Yes. And find the next action done by us. So here's the next action. The next input, the next configuration space was changed. Has the 5D offset, and also it has changed from 00 to 01. And probably we have additional routing settings. I believe the 19th line will be changed. So it's not interesting at this moment for us. We will look only to the configuration space and try to understand what's happening. Then we look more and more for our changes. There's a next change, and the offset is 62 in hexadecimal. And also the 00 is to change to 01. All numbers, all digits are hexadecimal. 63, I believe this will continue in the same manner. All other numbers will be increasing. Oh, now 5E. That's interesting. 5E. Done. 5F. Okay. 60. 61. Oh, and the next, interesting. All what we did is related to the analog outputs. So we see there are 8 outputs, and this is, as we see in the virtual machine, is this monitor output 1. The second is monitor output 2. Then there is analog 3, 4. Then there is headphones 1 and headphones 1 left and right. and headphones 2, left and right. Now we will look how does it confirm with the previously already decoded configuration space of the device. I will look the special file. It's in my project, Focusrite Scarlett backports, reverse eng, and config space. Here's the description of the configuration space of the device. When we see the set data message, it configures the internal configuration space of the device, which is split into two parts. The first part is reflected into hardware, and the second part is reflected is a persistent part, and is used only and is used by software only. So when the driver initializes the device, it reads first the hardware part and then reads the software part. Here we can see that this is the hardware part and the software part is at the tail of the hardware part. It is marked as a software config. I called it so. I don't know how it is called originally, but that is a persistent area, and I called it software config since it is used by software driver only. Anyway, we have an offset 5C, and this is related to monitor output 1. So we look at the row 50 and the offset 5C. And we can see here that this is related to mute section. As we see, we have 4 here and additionally 6 here. So we have 10. We have 10 bytes that allow to set mute for the hardware output or analog output of the device. Since the Focusrite 18i8 has only 8 analog outputs, not all of these bytes are utilized. So we need to look which of them are utilized. So we see that 5C is used, 5D is used, 5E, 5F, 60, 61, and 62 and 63. So we end up at this, and 2 bytes aren't used at all. Don't ask me why there is no strict order like this between inputs. I don't know. That's how Focusrite has wired the outputs, and maybe that was comfortable for them to do this, but this not straightforward numbering is a bit annoying. Anyway, we have configured our analog outputs, and now we need to see how the additional SPDIF, right? SPDIF and loopback outputs are configured. And here we see that we have the set data message, which is starting from 0 hexadecimal EC and is very large. But since we have captured the initialization sequence of the device, we compare the new message with the original state of the device and see that the only 1 byte at the offset 1B9 has changed from 0 to 1. So we need to write this. This is related to the SPDIF output 1. The next all additional messages also don't have any changes except The last one, here it is. This is the control sum or checksum of the configuration space, which is computed every time the configuration space is changed. So we don't need to have in attention this at this moment. So, and after that, we also have a message of configuring the routing of the outputs. The next one message. We have the same 1BD offset, 1B9 offset, sorry, and it changes from 1 to 3. That means that the state of outputs that aren't analog are stored in the bit mask. Each bit represents the mute state of the corresponding output. Our hypothesis can be confirmed by the following messages. So here is the routing, and the next configuration, or change from 03 to 07. That means that already 3 bits in this byte have been changed to ones. And that's related to the loopback, right? Right, to the loopback. And I believe there will be F for loopback too. Yes, there is an F. So all other outputs are numbered sequentially as they are seen in the interface. Now let's have a look into our short analysis at the 1B9 offset. And here it is 1B8. It is 4 bytes long. And here's the description related to the Focusrite 18i20 device. According to what I've discovered for the 18i20 device, the bits from 0 to 9 are associated with line outputs, from 10 to 11 with SPDIF1, 2, from 12 to 19 with A.1.1 to 1.8, and from 20 to 23 with a date from 2.1 to 2.4, probably. I didn't see any setting of it. And bits 24 and 25 are related to loopback. So this is true only for 18i20 device. So I need to change this description for 18i20. And here we can write new description for the device 18i8. So we have 0 to 7, there are line outputs. 1 to 8. Bits 8, 9 are related to the SPDIF1, 2. And bits from 10 to 11 are related to loopback 1 to 2. So we should remember this. And the additional information we can take. We can look at the routing again and see which lines have changed, which routing points have changed. So we just will take this and look what has changed in the difference watcher. So after, paste it here, replace. /n, replace. And now we can compare the before and after state. Okay, what we actually see here, all inputs have changed from PCM, mixture, or something other to off. Anyway, all as we see, the PCM 11 and PCM 12 are used by device for the loop back. What's the loop back? The loop back is the option that we can send additional signal to stereo or mono outputs of the device, and they can be driven back into the mixture, for example, or routed to somewhere at the output. So I believe it is more useful for mixing. So you can capture some sound, process it, and loop back as a loop back and loop back the process signal, and then mix it with the original signal and put them to some outputs. So that's how loop back can work. I never use the loop back, but I believe someone can use it. And for someone it will be useful. So we will probably look at routing in some other parts, and now we just need to look how the configuration is set in the driver. I won't take a long time for discovering. I just will take Mixture Scarlett Gen 2 device and look what is done here. There are probably read configs, USB init. So there's init private. We initialize the internal structure of the driver. Then there's USB init, initialization of the USB sequence. Then read configs. We read volume levels and control from the interface. Then add MSD, and then we're adding the controls. And we aren't adding any controls. If there is MSD mode on, when we disable the MSD mode, we are available to add additional controls. So there are line out controls, line in controls, and we are interested in line out controls. So we need to look at this function. So here's the volume control, playback, volume, software, hardware switch is not demute, and where are the mute switch? Yes, yeah, here's. Add new control. There are num line out. Num line out is a port count, Scarlett port type analog, Scarlett port out. There's a number of output ports. Okay, so we get this information from the descriptor. I believe there's 8 for the 18i8 device, and we doing a loop creation of the mute switches, and that's all. So we don't have any additional mute switches for these non-analog outputs. So probably we need to introduce new ones, functions. But before we can do this, we need to read the configuration area of the device and write functions that will do this. So we need to take the my version of driver and look how the software configuration space is obtained. So here's the additional function, Scarlett2 read software configs, and this is done after the Scarlett2 read configs is performed. So we need to copy and paste this to the driver. Okay. Scarlett2 read software configs has been copied, and now we need to find the implementation of this function. Here it is. What does this function do? This takes the private data of the driver as usual. It defines the pointer to the software configuration structure. It is not defined in new driver. Software configuration size. This is the size of the configuration, and we have already additional flag that shows us that the device has the software configuration space. For example, the 2i2 devices don't have the configuration space since they are too simple. They are too simple, and the comment, I think it's more useful on Windows because the routing is not as flexible as with Jack Pipewire. No, that's not true. I'll explain why. We have a Jack server, that's good. It allows us to route the signals, but before the signal becomes delivered to the software, it should be passed via a buffer. So we need to wait until the buffer becomes filled, and then we can read this buffer, process this buffer, form the new buffer to send to the device, and this buffer to the device should be sent. So we have some latency when working in such manner. So we need to wait until the buffer becomes filled. For example, it can be 64 samples or 128 samples or more. So the more samples we gather, the more latency we have. So we need to gather this buffer, process this buffer, ship this buffer back to the device, and then it will be played back. When using the internal routing, all the signal is routed at the real time without any latency. So it is very useful when you are trying to record some instrument, and you will get the least possible delay between what you play and what you hear. So that's why the higher level devices like I believe 8i6, 18i8 and 18i20 are more professional devices since they allow to do such monitoring. Yes, the low-end devices like 2i2 also allows to do direct monitoring. There's a special button on my device here, but that's not flexible. We can only hear one source, two source, or split into left-right. In the Scarlett devices, which are more pro, we can do all what we want inside the device. We can mix the settings. We can mix the channels. We can route the channels as we wish. And that's very flexible and very useful. You work with the device like with a mixture. and it is very useful when you work in the real time. I use this feature for recording guitar, and that's very, very useful feature. So that's not true that it's useful only on it is useful only on Windows. It also is useful on the Linux and on other systems when you want to get the least possible latency between what you play and what you hear. So let's go back and look into the function. So we check that the device supports the software configuration space, and then we call the function that allows us to read the configuration space of the device. I believe I also have written this function since the previous version of the function did another things. Didn't allow us to read something more complicated or read something with blocks. We see in the device driver that the configuration is split into 1040 byte blocks, and I think this restriction is not not so easy. That restriction has some meaning somewhere. So we need to transfer data not with larger blocks than the original driver does. So here we get the configuration, and then we get the size of software area. We allocate this space for this of the specified size, and then here we read the size only, and here we already read the original size as it is, and then we validate the configuration area size, dump it, and return. So we need to copy paste this function and place it somewhere. Oh, here's a calc software checksum already. Also, so we need to copy this function and paste it here somewhere before commits. Oh, there's some commit software config. Okay, and then interrupt volume change. Okay, we'll copy this before the interrupt volume change. Interrupt Scarlett to notify, it is called now, right? No, no, that's not. Oh, there is. I don't know the place where I should place it. I believe I need to look for Scarlett to USB get first. And I believe there's forward declaration of the function. Oh no. There's no forward declaration, there's just Scarlett to USB get. Okay, and what's happening here? We have some packet of the specified size. We call Scarlett to USB, and I believe this should be before Scarlett to USB get config is called. Okay, where's the Scarlett to USB get config? Here it is. Scarlett to USB. Okay, and what's here? Scarlett to USB get. And here's how Scarlett to USB get here. Okay. Here we see that the Scarlett 2 USB get was improved and allows us to transfer multiple chunks of the data to obtain their proper information. So we need to rewrite the Scarlett 2 USB get function with the new code here. We don't have this constant. We need to define this constant. Here it is, and we use 124 byte packet size, and it should be defined for the Scarlett port type and Scarlett port type before here. So we need to copy this constant here and move the comment below the definition. Okay, so now we can move forward and look back into Scarlett to USB get. Okay, and here I think I need to split it again and do this. I can close this. And close this part. And now at left we have old version of driver, the kernel version of driver, and at the right we have my version of driver. So here's my version, and here's the kernel version that we are editing. Okay, it's now pretty good, except that there should be a line drops disabled. So now that's pretty clear. And we don't have any Scarlett 2 USB set function. Instead of this, we have get configuration. 4 byte size parameters retrieved directly into buff. Something new here it is, but I don't think that these changes affect somewhere. These changes are new and they are proper. They allow to transfer large items and convert them from Little Indian to the CPU byte order when they are larger than 8 bytes. Okay, that's good. And then we have to copy paste the Scarlett 2 USB set function. It will probably be useful in the future. I don't know, is there any reference to the set? No, it's just new method that can be used in the future by us. So now we need to look where the Scarlett 2 USB get is used for loading the configuration space. Get config. Get config. Yes, that's right. Then next. Get volumes test and more. So we need to configuration space. No, not here. Also, I think we need this function dump config space. Dump config space, and it should be placed as Scarlett 2 gen 2 controls create. So we'll place it here. We'll place it here. Then I think, is there a for declaration? Yes, there's a for declaration of this function. So we need to copy it here. Oh, there's no for declaration more. Oh, I believe Geoffrey has reordered. What do we use in dump config space? Maybe we can move it at the top. Oh, there's Scarlett to USB RX and Scarlett to USB. So at least this function should be defined here. RX and USB. So I think I can copy it here. Oh, not right. Function. Dump config space. Here it is. And we'll copy here. This is debug function. We'll write the comment and we'll remove this function from the end of the file. That's good that Geoffrey has reordered the order of functions and we don't need any for declarations more. Okay, dump config space is okay. Now we need to read software configuration. Oh, there's commits software config and read software config. There are many calls by my driver, by my version of driver, this function, since it is very, very useful. And we need to copy these functions. And paste them somewhere at the top. I believe after the Scarlett to USB get, Scarlett to USB set functions. Here it is, Scarlett to config. This, oh, here. Request header, USB TX, RX, USB transfer. Scarlett to dump config space, USB get, USB set, and then commit software config and read software config. I believe I have already. No? Oh, here it is. And here's the call. Okay. Scarlett to read software configs and Scarlett to commit software config. The only left we need to Scarlett to software config structure. Here it is. And we need to copy and paste it somewhere at the top. Scarlett to data. Before the Scarlett to data, that's right. Here. Here I've left they're very not very. I left the explanation of each field. The only problem is that there are many constants and we need to check if these constants are present. So this constant is missing and we need to copy this constant. Here it is. I believe all these okay. I believe all these constants should be copied. Software config mixture on inputs, software config. All related to software config should be copied to the original driver. So it should be here. So I'll keep that. I think I will move the comments at the top. We have maximum 30 inputs per one mixture in the configuration. We have maximum 12 outputs in the configuration. I mean the mixture outputs. Maximum 12 mixture outputs in the configuration. Maximum 30 inputs per one mixture in configuration. What this? This is the offset of the field that holds the size of the software configuration. You can see that the original offset from the beginning of the device area, configuration area is F4. We can look into our description. Not that. Don't save. Here. I need to recall the offset F4. And here's the F4, the size of the software configuration area used by application. It includes the size of checksum, and the devices have value of 1984. So, okay, this is the. I need to copy the size of this. The offset to the field that describes size of software configuration area used by application. Not x4 0x4 0xf4 to minus 0xec. Software config stereo bits offset. There is, as you see in the device, you can switch from mono to stereo to the pair of inputs. So you can click here and switch to stereo and back to mono here. So the manner in which the driver will interact with the device is also stored in some space at the configuration area, and it behaves a bit different when we switch to stereo, to mono and back. So we just need to know this offset and we can use it. Oh, this isn't used in the driver, and this. Oh, that's nice. I don't need to copy these offsets at all. They are not used and I don't need to comment them. So there are extra, and there are garbage. The only thing I need to check which more constants I used here. So analog out max, other analog max. I don't like this constant name. I need to refactor and rename this constant. Analog out max and analog in max. So the maximum number of analog inputs is 8, and the maximum number of analog outputs. So I need to replace analog max with analog in max. Okay, that's good. Oh, and I don't like the missing spaces. I like when all constants are looking like table. I don't want to seek for numbers which are somewhere there. So I'll add extra spaces. So what's more are needed? What Scarlett in name lane? Oh, what's Scarlett to in name lane? I'll describe now. All in max. Do we have an all in max constant here? Yes, and here. No, we don't have, so we need to copy. What means all in max? It's the maximum number of all possible outputs. All possible outputs and all possible inputs. So we need to add these two additional constants here. This is the maximum number of all possible inputs for any device. For any device. So in namelane, what's in namelane? As we look, when we look at the Focusrite control center, we see the additional labels here. These labels allow us to mark some outputs with some naming. For example, this is KRK, Rocket 5 monitor. Oh, I don't have any more space. So this string is restricted with some length, and the length of this, the maximum length of this string is the constant, and I believe it's 12 or yes, it's 12 characters. So we need these constants too. Maximum length on the input of the label associated with of the text label, and the maximum length on the output name is the same associated. Maximum length of the text label associated with output name, with name of output, and here the name of input. All right. What's next? Which constant? Scarlett tool software config mixture inputs. I believe we already have this. I need to check. Yes. Mixture outputs 2. There are paddings. I don't know for what are there. There is a free space left in the software configuration, but there is a lot of free space left. I believe this is for extension or for future devices that can have more inputs or more outputs or more routings and so on. Anyway, here's our structure, and probably it will compile now well. So we need to check again. Scarlett 2 software config. Okay. And what we can do here, also we need to change the name of the structure since it has changed too. We have a Scarlett 2 data structure now, not Scarlett 2 Scarlett 2 mixture data. So we will rename the structure here. This is what? This is dump config space. Then USB get we don't need here. Or do we need here? No, we don't need it. Don't need it here. What would Scarlett to USB set? Probably no. Oh, read software configs here. The name of the structure has changed since I've written the driver. And here. Oh, Alpha, hello. Glad to see you here. I believe okay, here is okay, and we already have added to the call, and we need to already also check that we have the software config flag here. Has software config. I think the descriptor has no field. Yes, at this moment we need to add this field to the device descriptor. So we need to go the device info structure, and Scarlett 2 has mixture. I believe after that we can line out hardware volume, has speaker switching, has talkback, level input count, level input first, pad input count, air input count, phantom count, inputs per phantom, direct monitoring, line out remap and enable, line out remap, and I believe this can be inserted here. There is a spam in our chat. Area in the device is supported, I believe, supported. So, and we need to initialize all devices that we know that have the software configuration space with this flag. So here's the Gen 2, here are Gen 2 devices, and we need Gen 3 device. I believe all devices that have the mixture also have the software configuration space. So we will see that has mixture is set to 1. We can write the has software config to 1. I don't know about the Gen 2 devices. Do they have the software configuration space or not? So I won't change any Gen 2 devices, but I will change this flag for Gen 3 devices. Gen 8i6, I believe, will. So I can ask Alpha. Alpha, which Scarlett interface do you have? Does it have mixture inside of it or not. Probably Fanfa is here. Okay. Anyway. Oh, Alpha has 2i2 third gen, so as I. 2i2 doesn't have any internal mixture. Yes, you're right. I have 2i2 and I tested two solo device Gen 3, and they both have very, very small the device configuration space. So that's true. I thought you have 4i4 or 8i6 device. Yes, it has software control, and there are some features that allow to change, but there are not stored in the software configuration space. Probably you didn't watch the start of the stream, but I told that the configuration space of device is split into two parts. The first part is the hardware configuration, which is when you write the data to the hardware configuration space, it is applied by the device immediately. And the second part is the software configuration space, which is used as a persistence part for the driver which interacts with the device. So in our case, we are working over the software configuration space, since Geoffrey has done well with all the hardware configuration. We are working with the software configuration. Still, it will allow us to extend the behavior of the driver. So where 8i6 I will probably add has software config flag. The 18i8 without any questions has software configuration space, and the 18i20 also has software configuration space. I believe in the second generation of devices, all knobs were physical. So there is a push-pull knob, push-pull button, and all controls were controlled with the push-pull buttons. In the Gen 3 devices, all buttons are just clickable, and the software should control the state of different parts of the device. That's the main difference between the second generation and the third generation of devices. So we have added the software configuration flag, we have added the function, we have added the call that will allow us to read the configuration space, and we need to check if we have a dump of this configuration space. I think there is a dump. Scarlett calc software checksum. The format of software configuration header doesn't match the expired. Will proceed with significantly lower functionality. So, we also need a field in the side there, Scarlett data structure that will store the software configuration pointer to the software configuration area retrieved from the device. So we have the software configuration field, and we need to fill it. Here it is, and we need to copy this field to the configs, to the structure, Scarlett data, and put it here. I don't know why Geoffrey didn't left any comment about each field. I think it is understandable by the name of the field, by not always. I like to comment any field which I had touched. Anyway, I think we need to check where's the software configuration is initialized. I think there is a function there. Oh, dump config space, just status create. There was an initialization function. Oh, here it is. And here I need to Scarlett to init private. Yeah, here it is, and I just want to force to fill it with null. I don't believe that. Something will happen good. I think the best way to write safe programs is to reset each value to default at the initialization state in any way. So we will reset here it to null, and we need to free the allocated area when the device driver will be unloaded. So we need to check where the driver becomes disposed. Oh, also we have the checksum function. Do we have copied it? We didn't copy it. This is important since we need to compute the checksum of the configuration space shortly. The checksum is computed very simply. It just sums each double word or 4-byte block stored as little Indian block to one to another. So the configuration area, it interprets the configuration area as a sequence of 32-bit numbers, which are stored as in little Indian order. It just sums these numbers, inverts the sign of the sum, and writes it to some field. So when we will sum all numbers, including the checksum, we will get the 0 as a result. This is very simple checksum computation algorithm, and I'm happy that this is very simple. Reversing the driver with more complicated checksum computing will be probably more complicated. Thanks, Focusrite developers, for this simple checksum. So anyway, we'll get back, and we need to probably use beget. I've lost a bit. Read software configs. I need to check. Oh, here I don't like these tabs. I don't like these spaces. I probably need to replace it with tabs, but I don't see tabs. That's strange. I'll do this. We need to follow some code style used in Linux kernel. Okay. Now we need to dispose the driver, right? So I believe there's some function that will dispose the driver. Init notify. Where's the disposal function? Read configs, USB init, and private. KZ free, KZlog free. Oh, key free. USB init, key free. Scarlett to USB, not interesting. Set, not interesting. Enum CTLN phone, not interesting. Scarlett 2 private free. I believe this should be here, yes. And we have a software config and we need to free the software config. So we will just copy this here and extend. Also, the good manner is to write the null value to the to do the dispose pointer in the C code. So if you have freed some data, just write null to it. So that's good. So we have allocated data by reading software config. We have initialized the pointer when creating the device driver. We have disposed the memory allocated by the driver when the driver becomes deallocated, and we have introduced functions that read the software configuration space. So now we need to look how it will compile. Probably we've missed something. So I'll switch to my tough gaming laptop and run the make. It will be very, very cool if there will be no compile errors, but I believe there will be. I need to check again that the changes I've done have been applied. Custom kernel sound USB mix Scarlett Gen 2. So that's not the right kernel. That's my current kernel. I need this kernel. Not that. Sound USB and mixture Scarlett Gen 2 and look. Yes, we have our changes. That's good. It's with way. Okay, let's look. Scarlett 2 analog in max redefined. Okay, let's look. Max. Right. That's not in max. That's out. Oh, I believe I've made a serious mistake. Oh, yes. I've renamed it to the wrong constant. So look here and replace in with out. We don't need to replace this. We'll look forward. Yes, replace. Oh, the worst case that can happen, the kernel driver will panic and I need to reboot my laptop. So, yes, we'll replace. replace, 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 replace. Oh, and all. I need to check again where this constant is used. This constant is never used here and here. Probably will remove it once, but I'll keep it here. Okay. Which more rows we have now? Oh, all right. This is missing constant. Okay. Scarlett 2 device info has no member named config size. What's the config size? I need to check. Oh, not right. Copy, and here. Config size. Configuration space size for device. 0 for large configs. Oh, I recall what's this. If we try to read the more than available in the device, inside the device, we will get the wrong data at the output of the device. So we need to restrict the number of bytes that we need to read from the device. And this config size allows us to restrict the size of the configuration space. Yes. So probably we need to add this. And this field should be initialized for the Gen 2 I2 device, and 29 bytes actually are used. So we need to find the 2I2 descriptor and add the constant here, and solo. And solo has also 29 configuration bytes inside the device. I think it should be moved here, since we need to keep the ordering of the fields if it is possible. All right. Which more? Scarlett 2, USB get, implicit declaration of function. Okay. Let's look. Where we use the Scarlett 2 USB get? Dump config space, and then we have Scarlett 2 USB get. So yes, we need to move it a bit below Scarlett 2 USB set, and probably we can move it after the configuration read and write routines. And also, I don't recall how should it be indented here. Anyway, we'll keep it here now. So, which functions do we use here? USB get and Scarlett 2 dump buffer, dump config space. What's with dump buffer? Scarlett 2 dump buffer. We don't have any function Scarlett to dump buffer. Yes, we need to add this function here. Dump buffer allows us to print pretty readable state of the internal space of the device configuration, of the configuration of the internal device space. So I probably understood well. So these functions are debug only, but we probably need them. The dump config space. Is it called? Dump config space. Oh, it is not called. It is only called when it is necessary. I think we can add the dump of the configuration space after we have read it. So I believe we can do it here. And pass the mixture as a pointer to the handle of the driver. I believe we can try to build again, or okay, I think we need to run the make again. Oh, there are much less errors, so we can. Oh, there is an additional structure that we didn't implement, so we need to implement it. Here it is. And it should be before the Scarlett 2 software config. It should be defined here. The description of the volume, and this is done for volume settings. Okay, now which one more? The line 1239. Where's the line numbers? Where I think where are the line numbers shown? Oh. Oh, here, the line numbers here. So we need the line number 1239 or something near. Offset size. Oh, wait, what? buff redeclared as different kind of symbol. What's the buff? Buff. Oh, 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 yes. I need to check here. Yes, the not buffer, the data. Yes. And more. There is nothing known about data and bytes undeclared. Oh, we will use bytes instead of size. Okay, I believe now it will compile. I just need to launch again. And there's a warning that the function is not used. That's not the problem. We will use it extensively in the future. We'll just run make. And wait a bit. Yes, it seems that it has compiled. And now we can try to load this driver. Okay. Now we need to do a simple thing. We need to do rm mod. I need to do a ls mode first. Yes, we need to remove this module rm mod snd USB audio and mod probably back. Oh no, we need to rm mod. Then we need to copy the new version of module cp sound USB. Yes, SND USB audio KO. To the leap modulus Linux 5.15.22 RT custom I believe kernel sound USB. Yes, here. And we can check now that they are the same. The MD5 sum this and MD5 sum of that. Yes, they are exact the same. And we can now mod probably SND USB audio. And now I can enter the dmask. Yes, dmask dash w, and now I can connect the device to the laptop. All right. What do we see here? We see that the driver has requested the software configuration space, but I don't see any. Oh, I see the data here. Yes. All other data is reset to zeros, and that made me a bit confused. But we can see the checksum at the tail here. Where's the checksum? Or yes, here's the checksum of the device. So we have fully read the software configuration space of the device, and it seems that we did that right. So this part is the hardware configuration, and at this point starts the software configuration. We have read the full configuration of the device, and we have the unmuted inputs. Oh, I am unmuted outputs here. I'll need to check the offset again. The offset is at 50 in hex. So we'll get back. Here's the offset 50, and we have unmuted inputs. We can check now by disconnecting the device, changing the volume settings, and looking back to the software configuration space. So I'll need to switch the device back again. Now we can change settings of the device. For example, we can mute all and ensure that the configuration space has been updated. Okay, that seems to be enough. And we can switch now back to the laptop. I'll leave some space to ignore the previous messages and reconnect the device. Now we can explore the regions that we already have seen, and we see that all channels are muted now, all output channels are muted now, and also we have a 1B9 offset, which should have the F value 1B9. 1B9. Here it is. So we are properly working with the software configuration space, and that's good. And I think we need to commit the changes to the my forked version of Linux kernel. So I just need to make a backup of this driver and split commits in two parts. The first part I will rename the sound USB current gen 2 backup. I'll take from the git the latest version of driver sound drivers sound USB Scarlett gen 2. What's happening? Oh, I've copied. Yes, I can do this. How can I reload? File, did it reload? No, it didn't reload. I think I need to reopen it. Since I believe there is no I95 for the SSHFS MNT1 Linux Scarlett Gen 3 and sound USB. Oh, not that. This sound USB and SND USB audio or audio mixture Scarlett Gen 2. And we will start with just renaming this constant. Okay, that's enough. And we will commit this simple patch to the git. I'll copy this file. I need to check that all is compiling well. So I will perform make. And we need to ensure that each commit compiles well and doesn't destroy the kernel. So we need to check that it is properly compiling. No, it doesn't properly compile because I didn't rename the constant. Yes, I didn't rename the original constant, so we need to compile it again. Make. Okay, it seems to be compiled. It seems it has compiled, and I need just to replace it in the git tree and make a commit. Sound USB Scarlett 2. Yes. Yes, replace. Look git diff again. Yes. Git branch. Yes. Git commit. Renamed. Constant to this. Git add. Yes, and git commit. Yes. The first commit and the second commit, we need to remove this again to C and replace it with the original gain to C that we have made, and we need to reload it again. So close this and reopen. Is that driver? Yes. Only I don't like that space here. Okay. Yes. All right. Now I need to just replace this driver with new. Look for git diff. Okay, nice. Something here wrong. I need to remove extra spaces at the end. So, yes, save, replace, and git diff again. These extra spaces and these extra spaces has software config should be removed too. Do we have them here? Yes, here and here. And we need to place tabs here. All right. Do we have saved the yes, the driver? Yes. And now let's again copy git diff. Okay, that's good. That's good. I need to check again the Scarlett 2 software config structure, maybe offsets. Maybe I've used spaces instead of tabs. Oh, that's line wrapping. Disable it. Okay, that's pretty well. Oh, here, Scarlett 2 data need to be updated. Probably or not. There are spaces instead of tab. So I need to replace. Yes. Git diff. What's more? Okay. That's okay. Okay, I've changed the signature of the function. That's not critical. Here are probably some extra spaces that should be removed. Read software configs. Where are there? Well, here are extra spaces. Just remove them. Next. Oh, they're a bit below here. Uh, Here's the extra space, commit software config. Okay. Let's remove it. All others pretty well. So yes, now we can commit the new version of driver and add. Oh, the problem is that this commit contains the debug functions, but I believe I can change this commit after I finish the driver and remove these debug functions from the driver. So I will commit them with the other and just write the commit message git status git add git commit message edit implemented functions for reading software configuration of the Scarlett. Again, 3 devices and the names of functions. Read software configs and commit software config. Git push. Oh yes, it helps me to do what I want. Okay, I've pushed the changes and I probably can see them on GitHub now. Okay, I see that I've implemented the changes and they were pushed here. Yes, that's good. So I think we can end up this evening at this moment. If you liked the process, I will continue work in such manner and continue streams of writing device driver for Scarlett device. I hope it will be very useful for you. And if you know how to make my streams better, you can write comments and describe what would you like to see in the stream. So at this moment, I think I can tell you goodbye, or if you have any questions, you can ask now and I'll try to answer them. So I think we will take 2 or more minutes. It was very interesting. That's good. The main problem is that there were only 4 people watching this stream at once online. I believe I need to extend my my collaboration or my auditorium. So we need more subscribers. Please subscribe. Please write the recommendations what will be good to see in the next streams. So, and I think this is potentially good idea to provide the programming streams that allow to share knowledge, especially my knowledge, to other people and to get a feedback and learn something new from those who watch these streams. Anyway, if you don't have any questions more, I want to say goodbye to you and we will meet us on the next streams. Bye bye.